What's up, Eric?
Hey.
Crowd here. So welcome to the Friday Afternoon Physics Colloquium. Today's speaker is Dr. Kathryn Grimm, who's a professor at CSU East Bay. So Dr. Grimm began her academic journey as an undergraduate at UCLA. She got her PhD at Stony Brook, and she did a postdoc at Lancaster University, and is currently an assistant, I already said that, an assistant professor at East Bay. And today, she's going to tell us about highlights from current work at the Atlas Particle Physics Experiment. So, Katie, take it away.
Thank you very much for the introduction, and thanks for inviting me. It's nice to talk to you in Fresno. So yeah, I'm going to talk about some recent work from the Atlas experiment. So I'll first introduce the place and the detector a little bit, where this particle physics research is being done. And then I'm going to talk about a real mishmash of results, because I think I have recently been involved in sort of a variety of things, and I think that that's interesting, that sometimes you hear about one or two new advances that come out of Atlas or CERN, and there's really a lot of different things being done. So I'm going to do some various different things that are new results. And I'll talk a little bit about hardware work to build the detector. And then at the end, talk about using cookies to bring particle physics to the public. Okay, so first, maybe you've seen this picture. It's a aerial view of Geneva, Switzerland, where the Large Hadron Collider is. So this is the accelerator that we use to smash together protons. It's underground, so it's outlined here above ground. It's really huge. It's 17 miles around. And we need it that big in order to get the protons going really, really fast. And we want them to be going really fast because we want to create really high energies. So we want really high kinetic energies. And by creating that high kinetic energy, when we smash together the protons, we'll create a high overall energy that is similar to the energy that was present in the early universe, and is enough energy so that particles can be stable for just a fraction of a second that don't exist in our sort of relatively cold universe normally. So they're particles that exist.
Hang on, my brother's calling me. I'll call you back. Hold on.
That existed a long time ago, and that can exist in very high energy environments, either in an accelerator or sometimes in places in space. Okay, so that was my long-winded explanation of what we're doing at the Large Hadron Collider. Here's a little smash picture cartoon of where the protons get collided. So they're smashed together at 4 places along the accelerator, and at those 4 places there are big detectors that record what happens when the protons hit each other. So the detector that I am working on is Atlas, and that also Cal State Fresno is involved in. So what are we looking for? I said we were trying to recreate this environment of high energy that was present in the early universe. We're trying to understand what things are made of, what the fundamental pieces of the universe are. And this is a question that people have always had, so it's written in philosophies going back thousands of years, that people want to know what the world is made of at the most fundamental level. So people in Greece wrote down the word atomos to try to mean something that is indivisible, so something at the really at the core of what we see around us. So we want to understand both what is the most fundamental particles, what are the most fundamental particles, and then how do they interact in order to create our universe. So it's a pretty old and basic question, and here's our current answer. So this is what we think the universe is made of right now. It's made up of quarks and leptons and bosons. And in the quark and lepton category, the leftmost column are the lightest versions of those particles. And that's what we see most in our everyday lives. So the up quark and the down quark make up the proton and the neutron. So that's inside of all atoms. And then atoms also include electrons. And then if you have an unstable atom, it decays and releases an electron neutrino. So those are particles that we are present a lot in the world around us. A lot. There are many atoms. And then the other versions of the quarks and the leptons are heavier versions of these light ones, so that if there is enough energy, you can get charm quarks, strange quarks, top quarks, bottom quarks, muon leptons, tau leptons. So muon leptons are probably the next most common. Those come in the form of cosmic rays. So a cosmic ray proton will hit the atmosphere and it'll be so high energy it will create a muon. So those are also present in our everyday lives, although certainly not in the abundance of the electron. So then on the right, we have the force-carrying particles. So the photon, which we're familiar with light, the gluon, the force carrier of the strong force, the W and the Z, which are force carriers of the weak force, and then the Higgs boson, which I'll talk a little bit more about. So the bosons are a different type of particle, not matter, but they're responsible for holding together matter and for the other, for electromagnetism. Oh, this is my bad physics joke about you could have a weak password that might involve the W's and the Z's. You have a strong password, maybe the gluons. Okay, the other thing I wanted to say on this slide was that we want both to list these particles, the fundamental elementary particles, and we also want to describe how they interact to form the universe. So this description of how they interact is the standard model of particle physics. So I'll refer to that, the standard model. Okay, and how do these fit into the big picture of the universe? I said that this is somewhat related to being a time earlier in the universe when there was more energy. So this is a picture from the Young People's Book of Space, which I like. That is a timeline going from the beginning, the Big Bang time, to the present day. And you can see that in the present day, we have large structures like galaxies and planets. And as you go back in time, you get to a time when there were just these fundamental particles, just these elementary particles, before they had formed protons and neutrons, say, in this circle labeled 3. Before that, there were just pure particles. So in that high energy environment, there could have also been some of these heavier particles that we look at, like the Higgs boson or some other mixes of the heavier quarks, the heavier leptons, because there was so much energy. So some of the stuff that we're creating in the accelerator would have been present during that high energy density time. Okay, and so by studying how the particles interact, we can learn a little bit about how the universe evolved. Okay, so specifically today, I'm just going to sort of take a grab bag of new results. I'm going to talk about di-Higgs production. So I'll say what that means and why we're studying 2 Higgs bosons at the same time. I'm going to talk briefly about a new result that is photons interacting, which is not a common thing to study at ATLAS. And then I'm going to talk about quark-gluon-plasma, which is one of the early states of matter of the universe. First, I wanted to introduce Feynman diagrams. So this is how you write down how particles interact in particle physics. So if you look at the bottom right diagram, you can see here an electron and a positron coming together, annihilating and forming a photon, and then the photon decaying into a muon and then anti-muon. So the way that you read these diagrams is from the left to the right. So you have some initial state. That's usually what we put into the accelerator. Something happens, which we have to often guess at in the middle, and then we measure in our detector this final state, so the right side. So when we consider the interaction of particles in particle physics, we always talk about the mediator boson as carrying a force. So in this case, there's an electromagnetic interaction. We write that down as the exchange of a boson, as the exchange of a photon. So I'll show some more of these and I'll try to go through them, but I just wanted to show in general that you read them from the left to the right, and the thing that we measure is the thing on the very right. I like to put in these bubbles. Okay, so the first result I'm going to talk about, the di-Higgs production and Higgs self-coupling. So this is a thing that I'm working on a lot right now. And also Dan Brown at Fresno is working on this. I'm going to first talk about what the Higgs boson is really briefly, and then show some of the things that we're looking for when we look at two Higgs bosons. So this is just one way to describe the Higgs boson. So the way I like to think of it is in terms of the standard model as a set of equations. So when we said that the standard model describes the way elementary particles interact, so you can think of that in the same way that you would write down like the energy equation for a falling object. You could write down its kinetic energy and its potential energy. You could write down in another way how something moves based on its kinetic and potential energy. So like here's a pendulum moving. You can write down its acceleration as a function of its angle. Okay, so these are classical ways to describe how things interact and move. And then in quantum mechanics, you can write down a similar type of equation, the equation of motion for quantum particles using wave functions. So here's the Schrödinger equation for a free particle. So these sort of come together into an equation of motion, or Lagrangian, that describes how all of the particles in our chart, all of the elementary particles, interact using the different forces. So using electromagnetism, the weak force, or the strong force. So you can write down a similar set of equations that describe all of the interactions of the standard model. So that means if you have a positron and electron going in, you can use this formula to describe what is going to happen. And it's very successful. It's very accurate at predicting what will happen when these interactions take place. Okay, so one thing that this Lagrangian must do is it must be invariant under local gauge transformation. So what does that mean? That's basically means that the equations can't change under a transformation of the wave function. So you could just think of it as they must be the same in all locations and at all times. These have to be true always. And people found that when a mass term was added, so the particles in our chart have masses, except for the gluon and the photon, everything else has mass. And when this was incorporated into the standard model, the Lagrangian was no longer gauge invariant. So it basically didn't work anymore. We knew that the particles had to have mass, so that needed to be a component of the Lagrangian. But then it wasn't working especially in this gauge invariant requirement. Okay, so people didn't know what to do. Could the standard model just be wrong? But then Peter Higgs came along, and also Francois Englert, and they had an idea in order to allow these equations that were so successful at predicting what happens when elementary particles interact to also include the mass of particles. And that idea is now called the Higgs field. So here's a drawing from PhD Comics where they say, imagine a field that permeates the entire universe. Every particle feels this field, but is affected in different amounts. So this is the concept of the Higgs field, that you have a new field and it interacts with the particles, and that interaction gives the particles their mass. So by writing this down, basically by including a field rather than the direct mass terms, the Lagrangian for the standard model was able to be gauge invariant. So this was very successful. People thought this was a nice addition that could save the standard model. And then we needed to show that it was true. It was just an idea at first. So in order to show that the field exists, the Higgs boson particle needed to be found. So the field, if there is a field, there should also be an associated particle. And that is the thing that could be looked for. And that is the thing that was actually found. So in 2012, there was a big celebration that this new particle was found. And so it seemed to show that this theory of the Higgs field was correct. Okay, so since that time, 2012, when the Higgs boson was first seen, we've been trying to understand it, to measure all of its interactions with the other particles, and also to measure its interaction with itself. So that's what I'm interested in right now. So this is a little diagram of the Higgs decaying into two versions of itself. So this is a strange interaction, but it's something that that does happen. The Higgs particle can give rise to two of itself. And by looking at this, we can understand more about how the Higgs potential works and the Higgs mechanism works to give other particles mass. I'm going to talk about that a little bit more. So this, looking for this, I said before that the right half of the diagram is the thing that we see in the detector. So this is called di-Higgs production. You're looking, if you want to study this process of the Higgs decaying to itself, you're looking for di-Higgs production. Okay, so di-Higgs production can happen in a couple of different ways. The way that we really want is this lower diagram. So the upper one is two gluons come in from a proton, they interact with a top quark, and then they produce two Higgs bosons. But those are not the ones that are showing the Higgs decaying to itself, which is what we would really like to measure. So the bottom diagram is what we would really like to measure. Okay, this is saying again how that's related to studying the Higgs potential. So you can write down the Higgs potential, which is done here on the top. And it's a function of the Higgs self-coupling. So how often this interaction happens tells you what this potential looks like. People don't know that, so we think that it looks like this, kind of like a sombrero, but it's possible that it could, for instance, keep going, keep wiggling back and forth. People talk about that because if that were true, then hypothetically the universe could tunnel to another minimum and then bleep out of existence. So it seems unlikely, but it's possible, so we should measure it and then we'll know. It's one of the reasons to measure it. Okay, one blurb that there are other things that could create two Higgs bosons. So here on the right, I have a similar diagram where X is decaying into two Higgses, where X could be some unknown particle. So there are a lot of theories that say, oh, a new graviton or a dark matter candidate or something could decay into two Higgs bosons. So we look for that along the way as we're trying to measure the two Higgses. Skip the description of that. So This is the latest word on measuring di-Higgs production. So this is a paper I was involved with, which is really a statistical paper because it's the combination of previous results of people searching for two Higgs bosons produced in many different ways, added all together. So we yet seen this interaction of two Higgses at the same time because it's so rare. In fact, right now we're only being able to say that it does not exist at 7 times what it's predicted to exist at. So you could imagine that if the interaction were stronger or different than we think it is, then it might be larger than we think it is. So we have ruled out that it is not larger than 7 times what we think it is. So that actually was a very exciting result, even though it sounds like maybe it's a null result. We're getting closer and closer to being able to measure this, and when the accelerator is upgraded next, it will be a chance to really get down and be able to see the two Higgs bosons and see if we are living in the normal sombrero potential or if there is a more complicated interaction happening. Okay, and then I wanted to say one more thing because this is what Dan is working on. We're looking at this, I showed these production diagrams for making two Higgs bosons. There are a few other ways that you can make two Higgs bosons, and one of them is this one on the left that has the purple arrow. So in this case, instead of gluons interacting, we have quarks interacting, and then converting to what's written here as a V, which is a vector boson, so a W or a Z. And then that particle spits out two Higgs bosons. So what we're trying to do with the LHC is just measure how each other. And so one that we have not seen would be this into Z going Higgs parameter mode of the decay that is a little bit easier to see compared to background. So this is sort of something that we hadn't initially considered, but now seems to be possible to measure. So that's a fun new thing that, that we're looking at. Okay, so I'm going to switch now to my new the next bubble slide. So then the next thing I want to talk about is actually quite different, but really interesting. So usually the accelerator smashes together protons, but sometimes it smashes together lead. And when that happens, you get, rather than pinpoint interactions like these Feynman diagrams I've been showing, you get a new medium that is called quark-gluon-plasma. That is a soup of elementary particles that have a loose connection to each other, like in a plasma. So where a plasma is, I think protons and neutrons, quark-gluon-plasma is lone quarks and gluons smooshed together. And it forms a sort of blob that people are trying to understand. And this is a state of the early universe. People think that one of those states after the Big Bang was quark-gluon-plasma, so free quarks and gluons. There's an artist representation of it as sort of a fireball. So one of the ways to study this strange medium is to look for jets of quarks coming out of it to understand how those quarks interact with the medium. So here you can see on the right, two protons coming together and shooting out some quarks. So this could also happen when you smash together lead ions, but here you'll have this soup in the middle, and so there'll be different interactions, and you can compare the proton-proton collision to the lead-lead collision, and then learn something about the quark-gluon-plasma, the QGP. So I was a little bit involved in one of these papers just as a reader of the paper based on some really fundamental measurement that was happening inside. fundamental, I mean being related to the detector. So I'm not an expert in this, but I thought that the results are really interesting. So what is measured in these studies often is the ratio of what happens in the lead-lead collision to a proton collision, which is the normal running. So this is a busy slide, but what's shown at the top is the ratio R, is the ratio of the number of collisions in lead to the number of collisions in proton-proton, and then some factor that is related to how the nucleus is described. And then the result is that there's a big suppression of quarks when you have the presence of the quark-gluon-plasma. So you smash together the lead, you get this plasma, and then when an interaction happens, some of the quarks escape and some of them are sucked into the plasma because they interact so strongly with it. So the studies being done here have to do with how much the quarks are interacting with this new medium. So maybe I won't go into too much detail, but you can study all sorts of details about the way that the medium evolves, and it's like a football, and you can measure the shape. I'll just say one other thing. I came across this article that talked about quark-gluon-plasma possibly being formed when there are neutron star mergers, and that the trace of the quark-gluon-plasma might show itself in gravity waves. So I thought that'd be a crossover. Okay, and then the last little physics topic I wanted to talk about has to do with photons. So at the LHC, we're looking at protons hitting each other or lead hitting each other, but the thing that happens the most are strong force interactions. So on the left is a drawing that comes out of one of the Monte Carlo generators of protons hitting each other, and you can see the messiness of what comes out. So when quarks and gluons shoot off into space, they bring out other quark partners from the vacuum and make these showers of jets. And so you get a really messy environment. And so what we don't look at for majority of the time are single photons, but there's a new result from Atlas that is looking at that, at pure single photons that are coming off of protons. So the diagram on the right is showing two protons coming in, emitting single photons, and those photons interacting and forming two W bosons. So this is an interaction that would never happen classically. You wouldn't say that two photons, like two light particles, would hit each other and make two new particles, two W bosons. It's very quantum mechanical, and it's a particle physics interaction that had not ever been seen before in this pure state. So people were really excited about this, and the way that it was done was to be able to find the signature of the two W bosons coming out of the vertex of the protons hitting each other in a very clean and pure way. So you can see that this is a rendering of what's happening in the detector. As the protons cross each other, there are a lot of interactions that have particles shooting out. So that's what this mess of spider webs is. And we're looking for an interaction where there are just two very high energy W's that decay actually into leptons coming out. And so that's what's drawn in the red and the yellow. And then you can see in the picture sort of lower that the fact that the red and the yellow particles are coming out much further means they have a lot higher energy. So they had to find a whole lot of these very precise interactions in order to be able to study this photon-photon to WW event. And I was going to just flash that this is also a field of study that's done when you collide the lead atoms. So when lead ions are collided, you can also create photons that interact in various different ways, including in a way that allows you to study some axion theories. So I thought that was interesting that it was a big event both for proton collisions and lead collisions. Okay, so that's my sort of whirlwind of some flashes of what is happening right now in recent results. I wanted to also show what we're doing to upgrade the detector. Yeah, okay. What time did I start? At 3, right? Okay, so here's a picture of the detector. It's like an onion, so there's many layers of sensors. The particle interaction happens sort of where this arrow is, but we're way at the very center is where the protons collide, and then they explode out in all directions. And I wanted to talk about the innermost piece, the pixel detector. So I'm going to show you a little movie. There'll be a small delay as I get it going. So I just have to share the other screen. Okay, so I turned off the volume, but this is a video that's on the internet. So it's going into the centermost piece of the detector. And they're showing you as if you were a fly going right into the center of the detector. And you can see all of the sensors that are layered around the innermost part. So this is where the protons would hit each other. And this is what is in the detector now, and we're going to upgrade these pieces, but the technology is similar. So I wanted to show this to get a sense. So now if you pull it away, they're going to show us how a particle is detected when it goes into one of these sensors. Okay, so here we're taking off one pixel module. It's in 2 different configurations, so here's another one. So the one on the left is the pixel detector module, is the piece that is at the very center and that we are upgrading right now. So this is what I'm most interested in. So you take off some of the electronics, and what is under that, it's a layer of silicon and some solder bumps. So if you take away that top layer, these are tons and tons of little tiny solder bumps. And those act as electrical conductors. So if you have a charged particle from your proton collision that enters into the silicon, so now we're going deep down inside of the material to the atomic scale. So here's some atoms. So here's your charged particle coming in, and it hits the silicon atoms and it ionizes them. So it releases electrons, and those are the blue dots. So the blue dots, or the electrons, are free then, and they get sucked down into the solder bumps where they are electricity. So you have a little signal of electricity that goes through each solder bump, and that becomes a pixel. So then it's like a pixelated camera image. So that's how you get, that's how you pinpoint where your charged particle from the collision has hit the detector, is by noting which little solder bump got an electrical signal. Okay, so that is the current Atlas detector, and now we're trying to upgrade it. So I'm going to share back here. Okay, this is another picture. One of the things I wanted to say was, here's a picture where you can see the layers, electronic chip, bump, and then the silicon, so the material where the electrons are ionized. That material can be damaged by all of the radiation that happens in the collisions. And so one of the things we're doing is trying to model that damage, but we're also upgrading the detector in order to replace these pieces that are so damaged. skip the modeling of the radiation damage and talk about upgrading the detector. So this is the timeline for the upgrade. Because it's always being damaged by radiation, this is a really harsh environment to smash these particles at such high energies. There's always a program of upgrade. So this is starting from back at the beginning of the run of or collecting data, Atlas 2011. And now here today, we are at the middle here at 2012. So currently we're in LS2, long shutdown 2. So the detector is not taking data right now, it's being upgraded. And then we're gonna turn on again next year and start taking some more data. And then there'll be another shutdown, and then there'll be a really big upgrade, both to the accelerator and to the detector. And we're going to improve the detector both to replace the things that have been damaged by radiation and in order to be able to handle a more, a higher energy and higher luminosity environment of the upgraded accelerator. So you can see this little cartoon of the detector with particles inside it at the left versus at the right. So the higher luminosity, the LHC, high luminosity LHC, will be able to see more particles in a smaller amount of time. And so the detector has to be able to handle that higher flux of particles. So we're going to upgrade it to be able to do that. Okay, so here's, this is me and my student in the clean room at Slack doing some of this upgrade. So I put an arrow again. So we're looking at the pixel detector. Here's another drawing of the pixel detector. It's the very bottom part is what we're upgrading. There's a picture, again, similar to the video. So there's the silicon sensor, there's these bump bonds, the solder bond pixels, and then some electronics, and then some adhesive, and then the local support, which is just like the support that actually physically goes into the detector. So basically, what we're doing seems very unsophisticated. We are gluing sensors onto pieces of carbon fiber, and then those are going to go into the detector. So the thing that we're working on is gluing. So that involves choosing a glue that's radiation hard, and then programming a robot to put the glue in the same exact pattern on every one of these little tiny sensors, and then measuring extremely precisely that you have glued them on there correctly. The pieces that we're involved with are this glue robot and then this measuring. So I'll take 1 minute to talk about the measuring, because that's what we're super involved with. So this is the coordinate measurement machine. It's this big fancy machine that you program in order to make micron level measurements. It has either a touch probe or a camera. Oh, I actually skipped a slide. I meant to have one that didn't cover over what we're doing here, but we are, for instance, measuring the relative placement of these little tiny modules. And so one of the ways that you do this is you take a picture of the edges and create a new coordinate system that can define where your module is being glued relative to some beams near the place where they're being glued. So a lot of this work involves some geometry and figuring out how you want to reference things and what will move if you move your glue station. So this is interesting work that the undergrads have really taken over. So it's a nice project that everybody is working on. Okay. So I have time to talk about my final subject, which is cookies. So this is a project that I'm doing with another friend who's doing di-Higgs physics also. And we presented at ICHEP this year. So this year ICHEP was sort of in Prague, but it was actually virtual. They had everybody send in their photo and then make this collage rather than having a group picture. So this is an example of one of the cookie cake projects we're doing. So it came about with a team of Girl Scouts near Hayward, where we were talking, I was talking with these girls about what happens in the detector and how the accelerator works and what's inside of a proton. And we made cookies that represent protons. So here you can see a cookie with some gluon frosting and some up and down quark M&Ms. So this was successful in this small scale. That was like 20 people or something. So we brought it to CERN Open Days, which is, this was last year that we had it for, with real people in 2019. And they get like something like 50,000 people come to CERN over a couple of days. And they can go down into the detectors and then go around the site and learn about different elements of particle physics. And so we brought the proton cookies to this event. So you start with a plain cookie, people put their gluon frosting and then added the quark M&Ms, which we put in the different colors. So if you're familiar with the color charge of quarks, that was an element that we could talk about. Here's some pictures, so that was good for both kids. Here's some kids that said everything in the world is made of tiny particles, which I feel like that's great. That's good information. And here's some grown-ups and they say protons are made of particles called quarks. That's also great. So even though it's like a very simple sort of activity, you get some information away. And then here's a physics nerd who says a pentaquark discovery. So that's one of the new things that it's actually a particle that was sort of discovered and undiscovered a couple of times. People weren't quite sure if 5 quarks could bind together, but that is a thing now, 5 quarks together, either as some sort of quark molecule or as a new bound particle. So here it is on a cookie. And then we also brought the same activity to a group of girls. So this is called Expanding Your Horizons, and it's girls in the 11 to 14-year-old age. And another big event, so 400 people, and they also did the proton cookies. And it was, it's a nice way to involve people in discussion. So I just wanted to bring this up as like a kind of quirky side note, but I like to hear about people's ways of bringing in the public or people who are outside of the department in to learn about your research. So here's our cookie attempts. And then here's another example of some cookie physics. This is the Cal State East Bay students doing some Feynman diagrams with cookies. So I made this part of their final, that they had to choose particles that would actually interact in the standard model and no discovering new physics, arrange them in the appropriate way. So we have here, I think actually, so both pair production. So if a photon hits an atom, it can make an electron positron pair.
I was there.
Yay! That's right, you'd made it nice. I should have included your picture.
No, it's okay. I prefer you not to have.
Okay, so that's the end. Thank you very much for listening. I hope you have some questions from this wide variety of topics covered.
Thanks a lot. That was a great talk. Actually, so the cookie, so the frosting is the glue, the M&Ms are the quarks. What is the cookie?
Yeah, maybe it's like no, I don't know what the cookie is.
Wait, the background space-time, the underlying structure, the space-time. Well, anyways, all right. Let me.
Okay, we'll add that in.
All right. So anyone else interested? So anyone else have a question?
Yeah, Katie, excellent talk. So I have a question about the quark-gluon result. So how do our results from Atlas comparing with those from Alice?
Oh, that's a good question. So in my understanding, I have to admit that this is not the final particle or final paper that I was working on. The one that I'm working on is not quite yet public. And they are seeing results that are pretty close to Alice. So they're looking actually, this is showing jet suppression, and they're looking at the muons coming out of heavy flavor interactions. So heavy mesons producing muons, but it's supposed to match together with what's shown here, which is the quark or jet suppression. And they're showing results that are pretty much in line with what Alice has. So I know that there are a number of results that are not the same with Atlas, heavy ion, and Alice, but these ones that are about the suppression from quark-gluon-plasma are matching, and are also matching with the theory. So I feel like in heavy ion physics, the theory and the experiment are a lot more, one goes ahead and the other goes ahead. Whereas in photon-photon collision physics, I feel like the theory is very far ahead, and it'll take us a long time to catch up. But yeah, that result at least is in line with what Alice has. So Alice is the dedicated experiment that really focuses on this physics, and there's always a comparison then to see what they have.
Good to know, thanks.
So questions from the students?
Katie, did you know when run 3 will actually begin next year?
Yeah, that's a good question. I think that this is not too far off, but I know that there is some delay because CERN was shut down for almost 6 months. I think that there's still supposed to be some running next summer, but it might be more limited. So the normal turn on is to start running in May and end in December. And I think it's going to be shorter than that, but I think it's still happening. Maybe Yangsheng knows more. I think that was the latest.
Yeah, my impression like 2 months ago was also like sometime this summer.
Great, good. There's an awful lot of updates related to COVID, but I think in terms of the machine schedule, there haven't been as many, and I think it's still currently they're hoping next summer. And in terms of people going, I think it's still fingers crossed that we might be able to go next year.
Oh, and was there a difference as to how they accelerate the protons compared to lead?
Yeah. Yes. So they still go in, at CERN, there's a series of circles before you get to the largest circle. And there's a piece at the beginning of that cycle that is different for the lead ions. And basically you cut out the very first piece that is accelerating from the protons come from hydrogen that's accelerated along a straightaway, and the lead ions are in a different sort of shaped circle when they first start, I think. It's a very good question, and I think the answer is there is some difference at the very beginning, but once you get the lead ions going fast enough, they shoot into the normal same proton-proton accelerator. So once they're into the main LHC, then everything is the the same, except that there are fewer, so the protons are really often, and the lead ions are less often because they just don't need as many. They have so much that happens when one collision happens that they don't need them to happen as often.
Okay, so are there any other questions, comments? We want to know about the cookies. It's a cute idea, by the way.
Thanks.
Okay, well, if not, let's thank Dr. Grimm again for a fantastic talk.
Thank you, guys. It's great to, it's good to see people out in the world.
Okay, and so Yongsheng, you said you were going to stick around a bit.
But yeah, if you can, yeah, keep the Zoom meeting for like 5 more minutes, we can, Katie and I can touch base.
Okay,
Great.
and I'm going to go ahead and stop the recording.